What is going on, guys? Welcome back. In this video today, we're going to learn how to develop language models and how to work with large language models in Python. So what I mean by that is we're going to go through 4 different examples. We're going to start by implementing a character generation model in PyTorch. So we're going to do text generation in PyTorch on a character by character basis. The second example will then be a word generation model. So again, text generation in PyTorch using the attention mechanism, and we're going to generate text on a word by word basis. Then we're going to move on to the third example, which is going to be fine-tuning GPT-2, so a large language model using Hugging Face in Python. And the final example will be using LLaMa for text classification for sentiment analysis in Python. So let us get right into it. Alright, so we're going to cover quite a few things in this video today, and we're going to, as I already said, implement 4 different projects or 4 different examples, let's call it, where we're going to do text generation or text classification, where we're going to work with large language models. The first one, as I said, will be a PyTorch model from scratch, an LSTM neural network, which will generate text on a character by character basis. The second one will also be a PyTorch model from scratch, a recurrent neural network with a simple attention mechanism that will generate text on a word by word basis. The third example will be fine-tuning GPT-2 using Hugging Face. We're going to fine-tune it on a Wikipedia page and see the difference in output. And the fourth example, the final one, will be using LLaMa locally. So we're going to use LLaMa 2 because my computer is not capable of running LLaMa 3, I think. So we're going to use LLaMa 2, but I'm going to show you the process of doing sentiment analysis and by doing that also text classification using LLaMa in Python locally. Now, since we're going to cover quite a lot, I'm not going to go into all the details. I'm not going to explain every single line of code in detail, which brings me to the sponsor of this video today, because these examples and these projects here are based on a skill track from DataCamp. They're sponsoring this video today. And everything I show you today here in some form or another is covered in this skill track. So a skill track is basically a collection of courses and projects. What you can see here is that I didn't take all the courses. This is not because I didn't take all the courses, but because they updated the skill track. So there was a previous version of the skill track, which I took entirely. And now this is an updated version, which is even better because now they're even covering stuff like transformer models and reinforcement learning from human feedback. And essentially, what I'm going to show you in this video today is based on this DataCamp skill track. So you'll learn here about LLMs in general, you'll learn how to work with LLaMa, you'll learn how to do deep learning for text in PyTorch. Here you'll learn how to do text classification, generation. So they cover much more than I'm going to cover in this video today, but you can think of this video to be like a summary of examples or an application of a bunch of these concepts learned in this skill track. So if you are interested in more details, if you are interested in a slower approach where you learn from the ground up, the basics, what is PyTorch, what are tensors, how to work with it. If you want to learn it from scratch and you want to go slower, you might want to check out this skill track. What I'm going to do here is I'm going to give you the fast version of 4 examples based on this skill track. And you will, of course, find a link in the description down below. Make sure you check it out, and by doing that, of course, you can learn stuff and you can also support the channel, because this channel, of course, exists because of sponsors and because of you guys as viewers. So let's move on now to the first example. I'm going to go to my working directory, and here now I'm going to just make sure that Torch is installed. So just pip3 install Torch. This is going to install PyTorch, in my case already installed, and then we're going to open up a new Python file. Now, maybe before we do that, one important thing is I have a Shakespeare.txt file. Now, if I don't forget it, you will find a link to the Shakespeare.txt file in the description down below. Otherwise, it's very easy to find. This file exists on multiple websites, so just Google for Shakespeare text or Shakespeare.txt for machine learning, and you will find it, but hopefully I will include a link in the description down below. And then you can download it, and this is what we're going to train our model on, because we're going to build an LSTM neural network, so long short-term memory cell, which is a type of recurrent cell that has forgetting mechanisms. We're not going to go into the details here, but we're going to use that to do character generation, and hopefully the character that this model generates based on the training data will be somehow reasonable, will add up to words, and then these words hopefully also make some sense. So let us get started. We're going to say main py is our file, and now I'm going to start by saying import torch, then import torch.nn as nn, and then import torch.optim as optim. So nn is going to be for the layers, optim is going to be for the optimizer, and torch is going to be in general, for example, for defining the device. In addition to that, we're also going to import random. And then we're going to start with the first line, which is the device that we want to use here is going to be our GPU. If we have a CUDA GPU, if we have a supported GPU, we're going to use that. Otherwise, we're going to fall back to the CPU. So we can say torch device is going to be CUDA if torch.CUDA.is available, else fall back to the CPU. So in your case, you can run this as well. And if you don't have a CUDA supported GPU, it's going to fall back to the CPU. Much slower, of course. But if you have a CUDA supported GPU, you can just use it like this. And if you have multiple GPUs, you have to also provide colon, and then a number. So you get the device like this. And then we're going to open up our Shakespeare.txt file. So I'm going to say Shakespeare.txt in reading mode as F. And now we're going to load the text into our program. Now, since this is a pretty large file, I'm not going to load all of it. I'm just going to say file read, put everything to lowercase to make it easier, and then just pick the first, 200,000 characters. Now, if you want to have better results, you can include more of that text, but this is, of course, going to increase your training time. So the more text you use, the more it's going to take per epoch. The more epochs you have, of course, also the more time you're going to have to invest. But you can also just keep this running and, wait for a while, get some coffee or something. But we're going to keep it like this, 200,000 characters. And then I'm going to say here the characters that we have in this text are going to be, first of all, a set. Now, the set is in Python not like a list, but it only has each member once. So even if you have 1,000 A's in the text, it's going to just have one A in the set, because the set is only concerned with membership. Are you present in the set or are you not present in the set? So we're going to eliminate all duplicates. We're going to get every character exactly once by saying set of text. We then, however, want to turn this into a list. And we want to sort this list. Actually, we don't need to do both. We can just say sorted set. I think we can say sorted set of text. This should already typecast it into a list. And then we can get the vocabulary size, which is important for our neural network, by saying length of characters. Now, for our neural network, what we need to do is we need to take each character and represent it as a number, because the neural network doesn't understand characters, it only understands numbers. So what we're going to do here is we're going to define two dictionaries for mapping characters to indices and indices to characters. We're going to say character to index is equal to a dictionary comprehension character index for I see in enumerate characters. So we enumerate, basically adding an index to each of these characters, and then we map them. And then we say index to character is going to be equal to the reverse mapping. It's going to be index to character for CI in character to index items. So we just take this, reverse it, and then we have the reverse mapping. Great. So the next thing that we need to specify is how many characters do we need or do we want to take into account when predicting the next character. So our model is essentially going to be a next character predictor. We get a bunch of characters as previous context or as a sequence, as input sequence, and the job of our neural network is going to be to predict the next character. So how do we do that? We specify that we want to look at a certain sequence length. For this example, I'm going to use 100. So we're going to use 100 characters. We're going to look at the previous 100 characters to determine the next character. And the step size here is going to be equal to 1. This basically means that we're going to slide a window over our text, and we're not going to skip anything. We're going to, so for example, we're going to start with the text. We're going to take the first 100 characters, and then we're going to go to the next. So we're going to shift our window by 1. We're not going to jump 100 characters to go to the next 100 characters, but we're going to say, so maybe as a simple example before I explain this in an abstract way here, if I have A, B, C, D, E as input and my sequence length is 5, or let's say E, F, G, H, so I would start with the first 5, and then for the next training set, I'm not going to go to the next 5, but I'm going to go B, C, D, E, F. So I'm going to do a step size of 1. I'm not going to skip anything. And the data now is going to be a simple list comprehension. This list comprehension will be tuples. So I want to have a tuple for each example. The example consists of 100 input characters and 1 correct output characters. So I want to say here, the text starting from I is going to be 0 in the beginning. Later on, it's going to be, or we're going to do a list comprehension, so it's going to increase. But I'm going to start at a certain position. And then from this position, I want to go sequence length to the right. So that is the part that I'm going to look at. And what I want to predict is the character exactly at this position. So I plus sequence length. So this is one tuple. And we do that, of course, for I in range, starting from position 0 up until length of the text with a step size, which in our case is 1. But of course, we need to say length of the text minus sequence length, because we need to have 100 characters to look at. And that is basically it. I just need to close the bracket here. This is our data. And now what we want to do is we want to turn this data into tensors. So tensors are just like arrays, but multidimensional. And we're going to say here torch.tensor. And now we're going to get just the X data. So from our data, we want to get the X data, and we want to also encode it as numbers. So we're going to say here list comprehension, character to index of the character for character in sequence, for sequence, sequence and underscore, because we're not interested in the prediction in data. Now let's make sure we don't mess up the parentheses here. So that should be fine. And we want to put this to the device. Now all of the data, all of the models have to be on the same device. So we want to push everything to the GPU. So again, what we do here, we go through the sequence, or we go through the data. The data consists of tuples. The first element of a tuple is the sequence. The second one is the predicted character or the correct character. So we don't care about the predicted character. We only care about the sequence. So we iterate over the data, we get the sequence, and for each character in the sequence, we map it to the respective index, so to a number. And we do the same thing essentially now for Y. So we say torch, tensor. Here now we just need one list comprehension, character to index, character for character in underscore character. For underscore character in data. Because now, of course, we're only caring about the predicted character or the correct character that should be predicted. And because of that, we only care about this one from data. That is going to be our Y tensor. So this is now our data. The next thing that we need to do is we need to define our model. For this, we're going to say class chat LSTM. Or maybe we should not chat, sorry, character LSTM. Character LSTM, because it's going to generate on a character by character basis. NN module is what we inherit from. And we define a constructor. This constructor now is going to take a couple of parameters. We're going to pass here the vocabulary size, which is important because our prediction will be a probability for each possible character. So our output of the neural network will be a list of probabilities for each individual character that could be next, and we're going to just do a probability distribution, or we're going to pick from that probability distribution. So we need to have the vocabulary size. We also want to have the hidden size. This is going to be the number of neurons in the hidden layer, and we can say number of layers equals 1 for the LSTM, because we can specify multiple layers to feed the output into the next one and so on. We're going to keep it simple here. We're just going to call the super constructor, and we're going to say self. First of all, I want to have an embedding layer. Now, the embedding layer is so that the model can learn representations of the sequences. We don't want to just use the sequences or the indices right away. We want to learn representations. For that, we add an embedding layer. So we say neural network.embedding. Input is, of course, the vocabulary size, and then the hidden size. And then what we do is we say self.lstm is equal to neural network LSTM. Hidden size, since here the output is hidden size, here the input is hidden size, then the output of that is also going to be hidden size. Keeping it simple here, of course, we can choose different numbers as well. Num layers is going to be num layers, and we want to have batch data. So batch first is true. This basically changes the shape. So now the batch dimension is the first dimension. Finally, we want to have a fully connected layer. So FC is going to be a linear layer. And here we get hidden size, and the output is going to be, as I said, vocabulary size, because we want to have a probability for each of the possible characters. Now, the forward method here is going to be taking X as input. We're also going to allow for hidden as input. We're going to set it to none by default. Of course, don't forget the self keyword here, or the self object. So what we get here is the ordinary X and also a hidden state. This is important because we're going to use that for text generation. For training, it doesn't really matter. But we're going to say now, first of all, X is going to be equal to self.embedX. Then we're going to say output and hidden is whatever the LSTM gives us. So self.lstm on the output and on the hidden. So by default, hidden is none. So we don't have any hidden state to feed in here. We just feed the embedded input into the LSTM. As a result, we get output and hidden. Then we take the output and we feed it into a fully connected layer. So we say fully connected applied onto output. And here we select now, you need to think about it that way. Let me sketch it here. I'm just going to write it, then I'm going to explain it. So we have colon, -1, colon. And what this basically does is the shape of our output is essentially batch size, since we have batch first. Then we have sequence length. This is the dimension essentially. And then we have hidden size. So in order to get the last element here of the sequence, we need to say in this dimension, give me -1, and here give me everything. So we're basically getting just -1, the last element of the sequence. And we return out and hidden. That's it. Great. So that is our neural network. Now what we want to do is we want to create an instance of it. We want to say model is equal to character LSTM, vocabulary size, hidden size is equal to 256, for example. And we want to write this, or we want to put this also onto the GPU. Then we define the basic optimizer, which is the classic atom in this case. So optim.atom, we're going to go with a learning rate of 0.0003. So let's specify that we want to optimize the model parameters. The learning rate is going to be equal to 0.0003. And the loss function, so the criterion, is going to be equal to nn dot cross entropy loss. Also classic. And yeah, that's basically the setup. Now we can go into the training loop for epoch in range. Now I'm not going to define fancy num epochs and so on. I'm just going to type it right away. So 20 epochs here. And we're going to say model train to put it into training mode. Running loss is going to be what we keep track of, so 0.0. And then we're going to say for I in range. Now here we want to go from 0 to the length of the X tensor. And we want to jump batch size. We want to have a step size of batch size. Now batch size, again, we're not going to define it here as a variable. I'm just going to say 64 here right into the code. And then I'm going to say the X batch is going to be equal to X from I to I plus 64. Of course, in your professional code, you want to use batch size as a variable. So put this also to the device. Copy this, replace this with Y, replace this with Y, and then we have the batches. And now we want to make sure that the length of the batch is not 0. If it is 0, we want to continue. Otherwise, we're going to move on with the training. Now we do the basic stuff. We do optimizer 0 out the gradients. So 0 grad here to reset the gradients. Now we're going to say output is whatever the model predicts. It's going to also return a hidden state, so we need to have an empty placeholder here. We'll apply the model on the batch. The loss is whatever the criterion calculates, so we compare the output of the model to the actual Y batch, so to the correct prediction. Then we back propagate the loss so that we know where to go with each parameter, and then we take a step into these directions that we calculated. So the optimizer then takes a step into these directions. Running loss is going to be, we're going to add to the running loss here now the loss of this particular iteration. So we're going to say actually loss.item. And then finally, we're going to print here formatted string epoch I out of 20 in this case, or actually I plus 1, I should say, out of 20. And the loss is whatever the running loss is, because that's at the end of the epoch. So we have everything together, and we're going to round this to 4 decimal places. Great. So that is the training loop. Now, finally, what we need is we want to also have a generation function. So we're going to define a function generate text. This function will take a starting sequence, first of all, also the model, then a starting sequence, and then also a length. So it's going to get some input text, and then it's going to generate, in this case now, 200 characters of additional text. So we're going to say model, put it into evaluation mode since we're going to do inference now. And then we're going to say the input sequence is whatever we get, and we're going to now encode it again. So we're going to say torch, tensor, and then character to index of character for character in starting sequence. And then we're going to say tensor and then to device. Hidden is going to start as none, but now we're going to use the hidden state. We're going to say result is equal to start sequence, and we're going to say for placeholder in range, we want to generate 200 characters, so length. And for each of the characters that need to be generated, we're going to say now output hidden. Now we're no longer using a placeholder. We're actually storing the hidden value. And we're saying model applied onto the input sequence and hidden. The first time it's going to be none. The next time it's going to be set to whatever this model or the model outputted put out in this particular call here. So we get a result. We say the probabilities are now torch.softmax. So we apply the softmax function onto the logits, which is going to be which is going to result in values that all add up to 1. So we have a probability for each character. We apply this onto output. Dim is going to be equal to -1. This is again because our shape is batch size, sequence length, vocabulary size, and we want to apply to the last dimension. Then we also want to squeeze, so we have the dimension that we need. And then we're going to say the next index, so the predicted index is going to be sampling one item from that distribution, from this probability distribution. So we're not going to automatically go with the best or with the highest probability. We're going to do a sampling. So we're going to say torch multinomial, sorry. And we're going to use the probabilities. We're going to sample one item and we're going to get it. So that is the next index. So the next character, of course, is mapping this back, index to character of this next index. And then we say result plus equals next character. The input sequence is then going to be torch.tensor next index to device. Return result. Now, why do we only have the next index as the input sequence? Because of course we're using the hidden state as well, so we're still preserving the information. This is how you do it with LSTMs. And finally now we need to just call these functions. So we need to say print generate text, and we're going to provide the model and some input text. We're going to say he was going with, for example. And now we can do some stuff like, why is it? So very basic sentences. We must all, for example. And finally, if you want to, you can also save the model. You can say torch save so that you don't have to retrain it every single time. Save the state dictionary and provide a path like lstm model.pth. So probably I made some syntax error somewhere in the line here or some semantic error, but let's see if it runs, then we can talk a little bit about it. But I want to see the training loop started before I talk about this. There you go. You can see y is not defined. Did you mean y? Probably I mean y. Yeah, of course I mean y because y is lowercase since it's a vector, not a matrix. Okay, there is a problem, I think, with the epoch. So let me just cancel this. Yeah, obviously we don't want to do I+1. We want to do epoch, obviously. This doesn't make a lot of sense here to have the batches as a number here. So let's do it like this. Also, what I'm going to do now for the sake of this video to have it train faster is I'm going to decrease this to 50,000 instead of 200,000. And I'm also going to only train for, let's go with 10 epochs to show you what the training looks like. And then you can run it on your own system if you want for longer. The results are not going to be perfect. I can tell you that right away because this is a very simplistic model. This is not going to generate high quality Shakespeare text. It's going to generate some text. You can be already happy if it manages to generate words because you have to think about it. It generates on a character by character basis. So if it manages to have actual words in it, except for the ones that you provide in the beginning, that is already a success because you managed to train a model to generate actual words. But chances are that with 10 epochs, I noticed that I have here still 20, but it's still 10. With 10 epochs, it should be, I hope, decent. So there you go. What do we get here? Why is it I in... Yeah, okay, I mean, kind of. What do we get here? He was going with me gate preted of your such hit place. So yeah, the more you train, the more text you provide, the more epochs you train, the better this is going to get. But you can see we get at least something that looks like text sometimes. And your should, our, plays, do, will, think, one. Doesn't make a lot of sense. Again, you can see if you get better results by increasing that. I definitely got a little bit better results by using 200,000 characters and 20 epochs, but I don't want to waste too much time here now training while recording. So feel free to run this on your own. By the way, you will hopefully find also a link in the description down below to a GitHub repository with all the code, so you can just copy paste this, you can play around with it, you can tweak parameters and see what happens, but I recommend you go and learn this from scratch. On the one hand, of course, with the data camp skill track, but also by writing this out yourself, so don't just copy paste the code. If you want to really just write the exact same code, go and open it up on your second screen and then type it line by line so you see when you don't understand something, and then you can research. All right, so that is the first example. Let us go ahead now and create a file main2.py. This is going to be our attention-based model. We don't need anything additional in terms of packages, so we're going to again do the same stuff. Import random. Actually, let's even copy paste this. So let's go and copy paste all of this here. We're going to import the exact same packages. We're going to also use the same Shakespeare file. We're going to use the same device. But now we're not going to do character mapping. We're going to do word mapping. So we're now going to use word to index and index to word. So we're going to start by saying words is going to be equal to text.split. So splitting on white spaces. The vocabulary is going to be equal to sorted set of words. And word to index is going to be equal to a dictionary where we map a word to an index for IW in enumerate, not enum, enumerate words, or actually vocab, because we don't want to have any duplicates. There you go. And then we want to have index to word is equal to a dictionary, where we can say index to word for word index in word to index dot items. So just again flipping the other dictionary. Vocab size here is going to be also length of vocab. Quite simple. Sequence length now is going to be shorter because we're no longer dealing with characters. Looking at a lot of characters makes sense because characters are not words. When we look at words, it might make sense to just look at the last 5 words. I think this is a good value to get started with here. Of course, if you're building a large language model, the context window is much larger. But for our simple example here, we're going to use a sequence length of 5. And we're going to do something similar here with the data. We're going to say again, list comprehension. We again want to have a tuple. Tuple is going to be words from I to I plus sequence length. That is going to be the first part. And the second part is going to be words I plus sequence length. So here we're doing the exact same thing as before, but we're predicting the next word. Now, the challenge here is, of course, we have much more words than we have characters. So a word is, of course, longer, but that means that even though I only have maybe 26, or maybe if I have some fancy symbols, I can have like 50 characters, words I have much more than that because I have many different words that I can choose from. So we're going to have that for I in range 0 length words. And the step size is going to be 1. I'm not going to specify this now as a parameter here, but we again want to subtract the sequence length because the last section should also have 5 words in it. And then what we're going to do is we're going to again create a tensor. So I'm going to say again, x is equal to torch.tensor. We're going to do again the word to index of word for word in sequence for sequence and underscore in data. There you go. I think I'm missing a square bracket here. And then to device. And then y is going to be equal to torch tensor word to index, word for word in underscore word. No, I made the same mistake again. Underscore word in data, like this, to device. Same as before, just with a different dictionary that we're using for mapping. All right, now the neural network itself will also be quite similar, so maybe we can even copy the basic structure here from the previous file, but we're going to make some changes. First of all, we're not going to use LSTM. We're going to use an ordinary recurrent neural network here. But we're going to add an attention layer. So we're going to have here not LSTM, but RNN. It's going to be RNN here. Also, we're going to rename this to character RNN attention. We're going to pass vocabulary size. Here now I want to have embedding dimension and hidden dimension separately. We don't want to have num layers. I'm just going to specify 1 by default, or I'm not going to specify anything. We're going to have still the embedding layers. Still we're going to have vocabulary size, but this time we're going to go for the embedding dimension here. The RNN is then going to take the embedding dimension. It's going to produce the hidden dimension as the output size. We're going to keep batch first equal to true. And now we want to have an attention layer. Now, we're not going to use here some fancy query key value attention mechanism. We're going to use a very simple linear layer. So we're going to use, like, I think, additive attention. We're going to say NN linear hidden dimension 1. And then we're going to also say here hidden dimension for the fully connected layer vocabulary size. And in our forward pass, we're going to get the attention weight. So we're going to say here, first of all, we no longer need hidden. I'm going to say X is going to be embedded. Then we're going to have the output from, and also the hidden layer that we're not going to use, or the hidden information that we're not going to use, the hidden state from the RNN applied onto X. And then we'll want to calculate the attention weights. So attention weights is going to be equal to NN functional softmax. And we're going to apply this onto the attention layer. So we do attention on the output. We squeeze 2 dimensions. And we say dimension equals 1. So these are the attention weights now. And from this, we get the context. The context is going to be equal to torch.sumUp the attention weights. So attention weights.unsqueeze 2 times out dimension equals 1 again. So this now applies the mechanism onto our output. And finally, we want to just say output is equal to self.fully connected layer onto the context. All right. So again, since we're doing a lot of stuff in this video, I'm not going to explain everything in detail. For this, you can use the skill track of DataCamp. Again, for those of you who forgot about it here, let me just briefly show it again. Here you're going to also learn in this course about attention mechanism in Python in PyTorch. So they're explaining this in a little bit more detail. Great, so let's move on. Let's say model is equal to chat RNN attention. Here now we're going to say vocabulary size. Obviously, we're going to say 128 as embedding dimension, 256 as hidden dimension, and we're going to get this onto the GPU. And the rest is, or not the rest, but the next steps are pretty similar. Actually, there's no reason to copy this now because it's just 2 lines. So let's write it ourselves. Let's say optimizer again is equal to optim atom applied onto the model parameters. And the learning rate is going to be equal again to 0.0. Actually, here I'm using 1 0 less, probably because I got better performance. So let's go with 0.003. And the criterion is going to be equal to cross entropy loss again. So now let's do a training loop as before. I think for this one, actually, we can copy paste because it's basically the same and I don't want to type this out again. So let's copy the training loop from before. Copy it and paste it here. Now let's increase this to 20 epochs. Let's keep this the same. I think all of that stays the same. No problem here because that is agnostic to the model architecture. And the generate text method now is going to be different because now we need to, actually it's not going to be that different. Maybe let's see if I can, no, we don't have a hidden state, so it's a little bit different. So let's go and generate it or write it from scratch again. So generate text model start words numwords equals 20. So that's again the generation length. And we're going to put our model again into evaluation mode. We're going to say the generated text is our start words that we use here, all of them. Now, actually, I'm not sure why I did it that way. I either did it because I had a reason for it or I just got it from the DataCamp course. Not sure about this. Maybe we can just use start words. I'm not sure. But this is our already generated text. So this is what we give the model as a default. And then we go for underscore in range, number of words. We want to generate 20 words, so 20 iterations. The current sequence that we have is the generated text minus sequence length up until the end. So we go back sequence length words, then until the end. If the length of the generated text is already greater than or equal to the sequence length. Otherwise, if that is not the case, we're just gonna say generated in general. And we have to do some padding. So if the length of this current sequence now is below the sequence length, then we want to use padding. So we're going to say current sequence is equal to this character here, this nothing character, times sequence length minus length current sequence plus the current sequence. There you go. That's basically the idea. And then we're going to say index of the sequence is now going to be a list comprehension word to index of word for word in, or actually, first of all, we want to make sure that the word is actually part of the sequence. Otherwise, we're just going to return something else, because now that we don't have just characters, we can encounter words that we have never seen before. We don't want the model to break. So we're going to say if the word is in our dictionary, we're going to do that. Otherwise, I'm just going to say 0 for word in the current sequence. This is important because if you have all the characters, you can probably not have all the words or all the tokens that are out there. Because if I just enter something that's not a word, the model is going to break. So the input sequence now is going to be equal to torch.tensor. Index sequence, this is now all numbers. dtype is going to be equal to torch.long. We're going to send this to the device, to the GPU. And now we're going to say with model, with torch, no gradient calculations, so no grad. The logits are going to be model applied onto the input sequence. Logits are what we use for softmax to get the probability. So props are going to be equal to torch.softmax. By the way, no, that's fine. Torch softmax, and we apply it onto the logits. Dimension is equal to -1. We want to squeeze, and that is going to give us the probabilities. Now again, we sample from this probability distribution by saying next index is the same as before. Torch.multinomial. From the probabilities, pick one item and get it. And then the next word is going to be equal to index to word next index. And then we append this to the generated text. So we append the next word to this list of words. And finally, we return all these words joined onto a white space so that we have a full sentence, not just a list of words, or full text rather. And that should actually be it. Now I'm going to do exactly the same as before, but we're going to do it as a list. So I can copy this now from my prepared code because it's quite simple. We have the same text as before. He was going with, why is it we must all, but this time I pass it as a list, not as before here as a text. I pass it as a list. And I also specify number of words equals 30 to generate 30 words. And finally, we can do the same thing as before. I can get this from here now. Save the model, but this time we're going to call it attention model. So probably, again, I made some syntax error. Let's see. Let's run this and get an exception. There you go. Chat RNN attention. Chat RNN attention. What's the problem? Ah, why am I using chat again? Character, of course. I'm biased because of ChatGPT. What do we get here? Too many values to unpack. Oh yeah, sorry. We need to do outputs. Actually, let's also use plural. Outputs is going to be equal to whatever we get from the model. Now let's see, there you go. The training is quite fast. And I get he was going with your mind, the of person, the with your being gives the C's, okay. We must all of any, okay, that doesn't make a lot of sense. So it's also not impressive that it generates words because it's a word prediction. So it has to generate words, but maybe we can increase the training set here. We also have 20 epochs, so this is going to take now a little bit longer. But with these kinds of models, you can never expect something like a GPT-like performance. You can be happy if it makes somewhat sense. The more data you train on, the more complex your model, the better tuned your model is. The longer you train it, usually, unless you overfit it, of course, the better the results are going to be. So he was going with my nobler god, any, she, Bertram. She very well, she did her, yeah, I don't know. Why is it any alone? Okay, we must all any put false eyes from so foul. Yeah, doesn't make a lot of sense. But again, more training, more data will probably yield better results. More generalization is going to yield better results. But that is the general approach. You can now take this, again, hopefully from the GitHub repository and apply it to, first of all, of course, also different text data. You can take any text file that contains text or any file that contains text, and you can train a model on it. Now, I want to move on to the third example, which is fine-tuning GPT-2. Now, for this example, since this video is getting already quite long, I am going to explain the code, but I'm not going to type it myself all the time. So what I want to do here is I want to copy and paste sections, go through them while explaining them, and then you can take a look at them, play around with them. Again, you will find the code on GitHub. So because of that, I'm going to now open up a new file here, main3.py. And the goal is to see how the output differs from GPT-2, which is not the newest model, obviously, but how the output differs when we fine-tune it and when we don't fine-tune it. So what's the difference there? For this now, we have to install a couple of packages. So you want to open up your command line and you want to install, first of all, of course, PyTorch, then also transformers, then also data sets, and then also Wikipedia API. These three packages here, actually Wikipedia API has a different name. Let me just see what it is, because it doesn't seem to be that. Wikipedia-API seems to be the correct term. There you go. These are the packages. And we're going to use Wikipedia as an example for fine-tuning GPT-2 to generate text about Python. So we're going to start with the imports. Again, as I said, I'm going to do some copy pasting here. The imports are going to be the following: Torch, Wikipedia API, from datasets, import dataset, and from transformers. Now, this is important. We're going to import the GPT-2 LM head model, the GPT-2 tokenizer. So this is what we're going to use to tokenize text, to turn text into tokens. So not words and not characters, but tokens, which is something in between, we could say, parts of words or sometimes characters. And this is the model that we're going to train. This is a trainer. This is training arguments for the trainer. This is a data collator. This is, I hope this is how it's pronounced, collator, not sure how it's pronounced. But this basically batches our data, and this is the pipeline that we're going to run everything through. So the first thing that we define here is a couple of settings or a couple of decisions that we make in the beginning. First of all, our device again. Second of all, the model name that we want to use, GPT-2, the output directory of the fine-tuned model, the Wikipedia pages that we want to use for fine-tuning. In this case, I'm only going to use Python. You can also use other pages if you want to. And the generation prompt. My input is going to be Python is, and GPT-2 has to then continue generating text. And it's going to do that here with 150 tokens. So what I do now is I take the model, or I load the model, the pre-trained model from Hugging Face. So we say GPT-2 tokenizer from pre-trained GPT-2, from pre-trained here also for the model. Then we say, is there a padding token? If not, just take the end of sentence token as a padding token. And then we can define a basic pipeline. The pipeline is without any fine-tuning yet, so we just use the pipeline to say the base output is pipeline text generation, model being equal to the model that we created here, to the GPT-2 model. The tokenizer is the tokenizer, the device is our GPU. We provide the prompt, we provide the pad token and the max length, and this is going to return us then our basic output. So this already is enough to just generate the text without fine-tuning. Nothing else has to be done here. We just say Python is, and it's going to generate some text, but we want to compare it also with the text generated after fine-tuning. And for this now, I have some code that loads data from Wikipedia and prepares it into the right format. So I'm going to copy paste this here again. And you can see what it does is it uses the Wikipedia API. It uses this Wikipedia class here, says language is English, extraction format is extract format wiki. User agent here, you can provide whatever you want, but you have to provide it, otherwise it doesn't work. Then the text is empty. We iterate over the pages of this Wikipedia page, or we iterate over the titles. In this case, we only have one, but within that, we get the page of this title. We say if the page exists, that what I want to do is I want to replace all the double line breaks by single line breaks, and I want to say that if the length of the page is long enough, I want to add this text to the total text. So this is my text in general. Then I tokenize it. Then I say I want to have a certain block size, which is like a sequence length. And we say that we get the text and we truncate it or we round it to the nearest multiple of the block size. This is what is happening here. Then we take the tokenized text and we select the respective section. Then we split it into chunks and then we create a data set out of it. That's the speed run of this section here. The reason I don't want to explain this now in all the detail here, and I don't want to explain this, I don't want to take the time to explain this simply, is because that's just one way to get data into GPT-2. You can also use something else. You can load the data from a text file. You can do whatever you want. That is one way to prepare a data set for GPT-2. And now we're going to use this particular data set for training, for fine-tuning. So what I'm going to do now is I'm going to copy the section for the fine-tuning, which is the following. Training arguments is equal to training arguments. The output directory is clear. Number train epochs is how many epochs we want to use for training. Per device train batch size is going to be 2. Learning rate is going to be 0.000005. I think, if that wasn't 1 0 too much, not sure. Floating point precision 16 is if CUDA is available, it's going to be true. And then we're going to define our, whatever this is pronounced, collator. For language modeling, we're going to pass the tokenizer here. Then we're going to define our trainer. We're going to set the data set, the tokenizer, the batcher, let's call it. And then we're going to just do trainer.train, trainer.save model, output directory, tokenizer, save pre-trained into the output directory. This is now, of course, important because this exports everything and we need to then load it again with the same syntax as here. We're going to load it from pre-trained, but now we load it from our locally pre-trained models. So what I'm going to do now is I'm going to just do the same thing as above, but this time it's fine-tuned model is equal to from pre-trained output directory, tokenizer is from pre-trained output directory, and then we use the pipeline, text generation, fine-tuned model, fine-tuned tokenizer, device, same as before. And finally, this is now the final part here, we are going to output the initial generation, so base output 0 generated text, and then the fine-tuned output generated text. I'm going to store this. I'm going to say Python 3 main 3.py. This time I shouldn't have syntax errors because I copy pasted everything. We're going to get a bunch of output here that's not interesting to us, a bunch of warnings, a bunch of status messages. You can ignore all of this. This is going to now fine-tune the model, and once the model is fine-tuned, it's going to generate, and then we're going to see the difference in the default generation or between the default generation, which is going to give us some text that is somehow related to Python. And the fine-tuned version is going to give us something that's more accurate, but it's also not a copy-paste of the Wikipedia page. So it's not just going to give you the exact same text that is already there, unless, of course, you train it for too long. If you use too many epochs or a learning rate that's too high, you're going to get exactly the Wikipedia page, which is, of course, problematic. But if you don't do that, you're going to get a reasonable output that is better than the default. Okay, so we can see here the base model output says Python is hard to master, but it's extremely easy, whatever that means. I've already completed 5 projects for my latest game and some for this one. I can't emphasize enough how important this game is to me. I don't really know what this is about, and down here the fine-tuned model output is Python is a programming language with a large standard library. However, due to its extensibility, it's often referred to as an end-of-the-line language due to its high standard of grammar syntax. Yeah, I mean, yeah, several core features including metaprogramming and so on. So it is better, it is more suited, but it's not perfect. But you can see definitely there's a difference. This is much better, and if we fine-tune it on additional data, it's even better in terms of generalization. All right, now last but not least, I want to take a look at LLaMa CPP. So we can of course use Hugging Face for everything, but we can also use LLaMa locally using the LLaMa CPP package. So we're going to say pip or pip3 install LLaMa-CPP for C++ and Python, so -Python. And that is going to install a package which we can use to load LLaMa or the LLaMa models from gguf files. So you have these model files for inference. You can just load them locally, or you can load them from a repository, which is again Hugging Face essentially. But we can say here main4.py, and we're going to say from LLaMa CPP import LLaMa like this. And now we have 2 methods to load this. We can say LLM is equal to LLaMa dot from pre-trained if we want to load it from Hugging Face, or we can say just LLaMa, and then we can say model underscore path, and then the path to our, so we can say path to wherever, yeah, whatever. Path to gguf file. Let's put it that way. So that is if you want to do it locally. So you just have to have a .gguf file, or we can do it with the pre-trained version, which I'm going to do now here. So LLaMa from pre-trained, but this time we don't say model path, we say repo underscore ID. And here now I'm going to say the bloke, a famous repository or a famous person that has repositories, LLaMa-2-7 billion, so LLaMa2 7 billion gguf. And now we're going to say file name is equal to LLaMa2, so LLaMa-2-7b dot q2 underscore k, so quantization, and .gguf. That is going to select the model, and then we can provide a simple prompt for sentiment analysis. Now, I'm going to copy paste this because there's no value in writing the prompt. Essentially, I have here the prompt: classify the sentiment of the following sentences as positive, negative, or neutral. Sentence, so this is now a few shot example. This is the best pizza I've ever had, positive. The movie was quite boring and predictable, negative. The report is due by 5 p.m. today, neutral. I'm really disappointed with the customer service, and then we don't have a sentiment yet. So what we can do now with LLaMa 2 here is we can say output is equal to LLM, and then we can say prompt max tokens. In this case, we don't need a lot of tokens. We actually just need 1 or 2 tokens, but let's say 10. And we're going to define certain stop tokens. If we encounter these tokens, we immediately stop generation. One of them is going to be a \n, so a line break. Another one is going to be obviously sentence, if it starts with the next sentence, because it recognizes the pattern. And also if we get sentiment. So if it generates sentiment, sentence, or a line break, we're going to stop the generation. And also we want to set echo to false. Then we can get the predicted sentiment by getting output. From the output, we want to have the choices. We want to get index 0. We want to get the text of the choice. And then we want to strip this text. Then we can get predicted sentiment as an output here. Let's run this. And hopefully we get negative. So it loads the model right now. So this is an alternative if you want to use it. There you go, negative. This is sentiment analysis or text classification here. This is what you can use if you don't want to use LLaMa. If you don't want to use Hugging Face, you can of course also just point to a gguf file. That is how it was done also in the beginning and how you can do that for LLaMa with this particular package. So this was a lot of stuff that we covered in this video today. Again, as a reminder, this video was sponsored by DataCamp. These examples were based on the skill track developing large language models. Here you learn about the very basics of PyTorch, of LLMs in Python, of working with LLaMa, of doing deep learning for text with PyTorch. Also stuff that I didn't cover in this video, transformer models with PyTorch, reinforcement learning from human feedback, also LLM ops. So there's a lot to learn here if you want to take a slower approach and learn it in depth from scratch here. I think DataCamp has a very nice learning style. It's quite similar to mine, I would say, in terms of at least how much it goes into depth. They go into enough depth to not have you feel like you're just scratching the surface, but also they don't bore you with all the details when you get started. So I think it's a quite efficient way of learning. And as I said, they're sponsoring this video, so you would help the channel if you check it out. So you will find a link in description down below. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.